So I'm describing for you an experiment. Okay, it might be weird or not, but it's an experiment in which you have, I write boxes, but you have two systems in which you decide to perform two actions. Okay, I represent this action by this input. Okay, but again, it's like I do an action on a system and I get a result. I mean, this is reality, let's say, okay? Plus one minus. And again, reality won't create like this. Reality can be like, for instance, if you think about experiments that are done in my institute, they inject some light on the crystal, and the crystal creates this entanglement, and then they put some polarizers in two different positions, and they get clicks on some detectors, okay? But at the very end, I can abstractly represent this by putting these polarizers in two given positions, like call 1 and 2. I can call 1 and 2, and when a detector clicks, I call it +1, and when the other detector clicks, I call it -1. This is convention, but I can do that. And the experiment simply counts frequencies and computes these probabilities. There is no discussion about this. This is what you see in the experiment with your bare eyes, okay? So you don't doubt about this. You see it or you don't see it. And now what we theorists or mathematicians do, we try to represent okay, without sounding too arrogant, how nature behaves, okay? So we invent theories and we say how these probabilities are computed. And there are different ways. So with our common sense, and this is related to some of the questions I was getting, we will tend to assign, okay, there are some random variables, and then there should be a probability for these random variables, for these probabilities. This is, for instance, a way of thinking about this. Of course, if you start from this assumption, then you will never violate CHSH. Okay, so if you define a joint probability for A1, A2, B1, B2, you will never violate CHSH. This is proven. Well, this is simply telling you that this description does not fit the experiment, and you have to abandon it to describe this experiment. Okay, so you have to adapt your theory or your theoretical preconception of what happens in reality. So if you think that, okay, this A1, I should define random variables for the output when I use input 1, and the output when I use input 2, and the output when I use input 1, and the output when I use input 2. And there is a joint probability for all of them. In this description, you don't violate Bell inequalities. And since you violate the Bell inequality, this description does not explain your experiment. Okay. And then your description is falsified by your experiment. Okay, I'm not sure if this is helping you or not. Maybe it's adding more confusion, but... Okay, so I was telling you about these sets. And then I was telling you about the MPA that approximates this. Now, I will go back to my initial motivation, which is how to certify a random number generator. How you can be sure about something behaving in a random way. It seems like contradictory, no? You're certain that something is random. But this is possible, okay? And this is what we show. So basically, it's like you can think of the scenario I was telling you. You have a web page with a virtual casino, and you want to use a random number generator that cannot be predicted by anyone on Earth, no? Because otherwise, this person will get your money. So for instance, I don't know if you know this story, but in Spain, there was a family, there is a book and even a movie about this family. They are called Los Pelayos, okay? So this is a family that they went to casinos. At that time, I think it was in the 60s, 70s. In Spanish casinos, they were using a roulette, and this family realized that this roulette had a pattern. It was small, but the family was large. So they were sent to these casinos, and they were getting money. Why was that? It was because the owner of the casino was that the roulette was random, but the Pelayos knew that the roulette was less random than what they thought. Okay? More predictable. Okay? So we want to avoid these situations. We don't want that someone has a better knowledge about us, about a situation, and can get this for its advantage. Okay? So the fact that you see something that looks random doesn't mean that it's random. Okay? So, I mean, the guys in the casinos, they thought that the roulette was fully random, but it was not. So people realized of these Pelayos, and at some point they couldn't enter Spanish casinos for some years, okay, because they were cheating. Well, cheating. They were not cheating. They were betting and getting money, but they realized there was a pattern in the roulettes. Okay, so we want to avoid these situations. I want you, I mean, in the extreme case I was telling you is the one in which you have your virtual casino, and I'm selling you this memory stick. You remember, we want to avoid this situation in which the memory stick things are written and they look random to you, but they are not random to me. Okay, so this is what we propose. This paper some years ago, already some years ago, yes. And basically what you have to do if you follow what I was telling you, if you want to have a proper certified random number generator, you have to ask for a Bell test. Okay, so what you have is you want to have a random number generator, you run a Bell test, which is something that you can do in a device-independent way because you only need to compute the expectation values of A1, B1, A1, B2, for instance, in the CHSH, okay? And then you can take the output of a Bell test as random bits. And you can prove in quantum physics that these numbers are unpredictable, not to you, because you have no clue about what is happening, but to any quantum physicist on Earth. So if you want to have an intuition of why this is happening, is because if you violate this, it means that no one can predict the outputs of your experiment, okay? Because if you have a Bell test and I can predict what are going to be the outputs of your experiment, I can write them down, I can predict, right? So I can say, okay, if you measure 1, you will get +1. If you measure 2, because I can predict them, no? If you measure 1, you will get +1. If you measure 2, you will get -1. If you measure B1, you will get +1. If you measure B2, you will get -1. So the mere fact that I can write these numbers means that CHSH cannot be larger than 2. Okay? Because if I write them, as soon as I write them, this quantity is bounded by 2. So the Bell inequality is telling me that no one can predict my numbers, because if this person could write them, and this quantity will be bounded by 2. Okay, this is the intuition. You can make this intuition quantitative. And basically what we did in that paper, we found a relation between the Bell inequality violation and the predictability that someone can have on the outputs of a Bell test. So remember, the outputs of a Bell test are two output outcomes, two value outputs, okay? And so the predictability can be, in the best case, can be 1. In the worst case, can be half, okay? If you know nothing, if you make a guess, you will be right with probability half. Okay, this is a random bit. And then you can prove as a function of a Bell inequality relation what is the best predictability a quantum observer playing with all possible Hilbert spaces, doing whatever this person wants with the devices, still quantum, how much this person can predict the output. And well, perhaps not surprisingly, if you have no Bell inequality violation, you are the local classical bound, your predictability is 1. But as soon as you start violating this Bell inequality, then the predictability decreases, and at 2 square root of 2, the predictability is half, that is a perfect random bit. So the randomness of the outputs is certified by the Bell inequality violation. This region is impossible in quantum physics. And how do we exclude that? Is using this MPA outer approximation. Okay, so all the points here violate MPA, therefore they are not quantum, therefore they are impossible for a quantum eavesdropper.
Do you know the equation of the curve?
Yes, we have it. In this case, yes, it's the square root of, well, no, it's the square root. Okay, yes, I can, yes. So in this particular case, you remember I was telling you that MPA is a outer approximation, but there are some cases in which it's tight, okay? In this case, it's tight. So you can run MPA, you have a curve here that is an upper bound, and we gave a concrete quantum realization, so you close the gap, and in this case, we can derive it. It's a simple problem that we can solve. And it happens that the solution you find is the optimal one. Okay, so you have, in quantum physics, if you use a Bell inequality relation, you can be certain about randomness, and this is what we proved. Okay, so you can bound the randomness of the outputs from the Bell inequality violation, and you can apply this not only to CHSH, basically to, we have techniques using this polynomial optimization that I'm going to give more details now, that you can use to bound the randomness of outputs in a Bell test. Now, my initial problem, however, was for QKD, for quantum cryptography. Well, I don't have time, but you can use the same techniques to make a protocol. Okay, randomness is a single user protocol. You go to the provider, the provider gives you 2 boxes, and you run a Bell test in your lab. Okay, and then you know that, okay, I will use the outputs. You can use both outputs, actually, to generate random numbers. In cryptography, Younes and I, we go to the provider, we get the 2 boxes, and we have to run a Bell test at distance. This is not easy, but in principle possible according to quantum physics. And then you can prove that out of the Bell inequality, the probabilities, the correlations violating a Bell inequality, you can make cryptography. Okay, you can make a security proof, and the security proof is only based on the observation of these statistics. So there is, if you remember what I said, there is no mismatch between what you require in theory and what you see in the experiment. Okay, because all what you require in theory is the observation of a CHSH value, and what you see, all what you see in the experiment is the observation of a CHSH value. Okay, so this is a situation in which we use a lot all this non-commutative polynomial optimization, which is MPA, and this is what I'm going to tell you now with more details in what follows, okay? That was a very long introduction and motivation for the use of these techniques and how we arrived to them. Victor explained polynomial optimization. So basically, in the classical case, what we have is our variables. We have polynomials subject to some positivity constraints on some other polynomials. Okay, and then well, he explained, I believe, the hierarchy and how you have a sequence of lower bounds to tend to this minimum. Okay, so yes, I guess Victor explained this. I'm assuming that you saw all these things. Okay, good. So now we are doing something, basically we are replacing numbers, commuting variables by non-commuting variables, so they become operators, arbitrary operators. And we have an eigenvalue problem, so we want to minimize the expectation value or the overlap or or the eigenvalue of this polynomial of some operators, and who are subjected also to some constraints given by polynomial over some operators. Okay, so this is what we are doing. And basically what we have is that, okay, this is the first thing I was telling you was, the first paper was in the context of this characterization of quantum correlations. Then we made things more general. In the end, I think most of the things I'm going to tell are in this paper, okay, in which we connected with all the literature on polynomial optimization. So it was funny because at that time we didn't know anything about these things. And then we knew about the papers by Lasserre, and then Lasserre was nice. We visited him in Toulouse, and we shared, and we learned a lot from all this hidden world for us about polynomial optimization. And okay, basically what we have is that what we do is similar to what you do in the classical case. So you have monomials made of your operators. In that case, things don't commute, so you have more monomials. Okay, so when that's here, you have a monomial, and you have also some that, I mean, depends on whether they are self-adjoint or not. In quantum physics, in many occasions, they are self-adjoint, the operators, but they don't need to. Okay, so here, for instance, I'm just representing this monomial in which, okay, you can represent by any index, no? So this is x1, x3 complex conjugate, and twice x6, okay? This is a representation of the monomial with some index. And we consider maps from these monomials to complex numbers. And then using these maps from the monomials to complex numbers, you can construct what is called the moment matrix. You all know these things, right? Okay, probably better than me. Okay, so, okay, then you can construct this moment matrix, and also for polynomials, and later they will be also positive polynomials, you can define the localizing matrices. Okay, you see here, you have the monomial, the polynomial made of some monomials, and you construct with the same linear map, you construct the localizing matrix. And okay, the moment matrix I'm defining here, you can see it as the localizing matrix for the polynomial identity. Okay, so this goes away and you have back to what I was telling you before. And okay, what happens is that if your linear map has a quantum form, okay, it can be written as what in quantum physics we say the expectation value of some operators acting on a quantum state. So basically what I'm demanding is this map from monomials to complex numbers has this form. Then it's simple to see that the moment matrix is positive and the localizing matrix is for positive polynomials. I guess I can assume this is straightforward for you. No? Okay, so maybe just... Okay, so what I'm doing is the following, okay? So you have some operators, and you can construct monomials out of these operators, okay, for this case. So now you pick up a set of monomials, okay, for the time being arbitrary. And then for this, you define a linear map from monomials to complex numbers. Okay, this is what I'm doing. And then from this linear map, I can define the moment matrix, which is, you see, I take the alpha, beta, I label my rows and columns by this index. And then the alpha, beta element of my matrix is given by the linear map acting on the corresponding monomial. Okay, you see here, here I'm labeling by 0, 1, 2, 1 bar, and 2 bar. Okay, so these are the indices of the monomials. And then here I will put for each element, I will have the corresponding monomial, and I will apply the map to the corresponding monomial, and this is the way I construct the moment matrices.
This thing that you also consider the adjoint, should we think of this as an doubt variable, like completely?
Well, it's not independent, but it will grow the size of my moment matrix, but it's not independent.
So you have like the set of monomials twice?
You have more monomials, yes, because you have but they are not independent. They might be related. Yes, because I have this possibility. Yes. For instance, here in standard situation, you would never have this 1 bar. Okay. Yes, exactly. So basically, you have things grow because you have non-commuting things, and you have yes. Although in quantum physics, often you have self-adjoint things like projectors or what is called observables. In quantum physics, they are self-adjoint, if you know what. Okay, and then you may have also some constraints in terms of other polynomials, and you will demand that these polynomials are positive, and you can also define the localizing matrix in the same way. Okay, you see here, you put the alpha beta element, you put the alpha beta monomial within the polynomial that you are giving for the constraint. Okay. And now, if you have a mapping that has a quantum form, then you can prove that all these matrices are positive. Okay, I'm not going to do it, but it's not. It's something that is not difficult to prove. Okay, so this is the problem you want to solve. Okay, remember, this is a quantum problem you want to solve. And now I will replace by this problem. Okay, so this will be a map. I will replace the expectation values of monomials by numbers, and I will demand that the corresponding matrices are positive. And I will do this. I cannot do it for all possible monomials. I will do it for a subset of monomials. And then this is why it's an outer approximation. It's a relaxation because I'm not taking all possible monomials in my theory. So this is all what we do, okay? And the more monomials you put here in the definition of the moment matrix, the localizing matrices, the closer you get to the solution. And this is why you have a sequence of lower bounds, and you can prove that it is convergent under some mild assumption conditions on the problem. Is it clear what I'm doing? Do you have questions about this? I mean, if you follow what Victor was doing, it's more or less the same, but with more terms because of non-commutation. And okay, then I don't know how much Victor say, but what you can prove is that somehow if the operators are sort of bounded, okay, in what is called the quadratic module, then you can prove that in quantum physics, many problems satisfy this condition because, for instance, if you have a projector, projectors are bounded operators, so you can have things. Okay, it's very unusual that we work with unbounded operators in quantum physics because usually they are associated to unbounded energy but okay, we can prove under which conditions the hierarchy converges. There are some situations in quantum physics in which the hierarchy does not converge. For instance, if you know about bosonic systems, this is a situation in which the hierarchy does not converge. But okay, we have some control, and if some conditions are satisfied on the operators, then we know that the hierarchy converges. Okay. Now, the proof of convergence, the first proof was it was mostly Miguel Navasquez, who was a student in my group at that time, together with Stefano Pironio, who found the proof, and the proof goes from the primal, from the definition from, say, we work in this, say, level, okay? But we learn from polynomial optimization people that you can also go through the dual, okay? And then you define the dual, and the dual looks, I'm assuming that you saw these things, okay, or something very similar. So it looks very similar to what I was telling. Maybe this is, yeah, this is okay. No, maybe it's the opposite. No, it's okay, no? Yeah, okay, you can find also the, I'm not sure if this is correct, but okay. Okay, you can define the dual problem, and basically what you want is the difference of these two numbers has to be a sum of squares, but now given by the operators. And you can prove that this is the dual, so in one case you have, this gives you a lower bound to the lower bound that you have, and you can close with these things, and you can actually solve this in the standard SDP formulation. Okay, so sorry, something that I forgot to say is that this is an SDP, okay? The relaxation, because you have a linear constraint. This is given by your problem. These are coefficients. These are your unknowns. So you have a figure of merit that is linear on your unknowns. And these matrices depend on these coefficients in a linear way, and you have operator positivity. So this is a semi-definite programming, all the relaxations. Okay, so basically this is telling you that using these techniques, you can find a sequence of lower bounds that tend to the solution you are interested in. Now, in the case of Bell inequalities, it's more a feasibility, but you can turn it, okay, if you want to find the maximum. In the commuting case, you will have an exercise on that, but if you want to find the 2 square root of 2, okay, this is the polynomial you have to solve. Since these outputs are equal to plus and minus 1, these observables, the square has to be equal to the identity, and in the commuting case, all these observables commute. All those are polynomial stuff, and then you can address this with the techniques we had, okay? And here you want to find, remember, this is the beta quantum that is 2 square root of 2. In this case, the first level of the hierarchy already gives you 2 square root of 2. So it's a situation in which you don't need to go to infinite level. At first level, you already get the quantum solution. Okay, so this is any problem in which you are interested in a Bell inequality for more, I mean, this is CHSH, but you have more measurements, more output, you can still play these tricks and you will get an outer approximation to the quantum solution. I'm going faster here because I thought this resonates more with the stuff you know, but. Okay, and in this case, these are things that we learned also from Toulouse, and you can connect with all the literature on non-commutative positive length sets. Okay, and there is an analog of the classical result for non-commuting operators, and you could also prove convergence using this dual formulation. Okay, so I think it connects very well with the stuff that was known in the optimization, classical polynomial optimization. Okay, and basically what you can see is that when the problem becomes classical is when you demand that all operators commute. Okay, and then the non-commutative version becomes the commutative one. Okay, you can prove that if you demand that all operators making the monomials commute, then you are back to the standard polynomial optimization. And it's somehow funny, and the exercise will be on that. I mean, sometimes things are quite different. For instance, in case you have polynomial over projectors, the first level gives you the value, it's easy, but if you take the commutative version of that, this is a standard quadratic and it can be a quadratic unconstrained polynomial optimization, and this is NP hard. Okay, so sometimes the non-commutative version of some problems is easier than the commutative one. Okay, so it doesn't mean that this is a particular instance in which this problem is known to be NP hard in general for some polynomials, and this is easy for the quantum case, for the non-commutative case. Okay, do you have questions for this part? Yes. Here, yes. 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 A1 and A2 don't commute. Yes. 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 Yes, exactly. So for instance, if you run this, no? And you will also impose things like this. You will get 2. Okay, because you are back in the classical world, yes. Okay, in some cases, yes. In general, no. So if your experiment in CHSH, the first level gives you the quantum value, and you can extract the realization from the CHSH, from the moment matrix. Okay. This happens for some particular cases of Bell inequalities. You can extract the state and the measurements, giving you the quantum realization from the moment matrix. But in general, this is not the case. It's quite hard. Because a generic problem, okay, so since the problem is undecidable, we know that there are instances of the problem in which you will need to go to the infinite level of the hierarchy, okay? So we know there are situations that are pretty bad. But sometimes even if you, okay, so basically what we do physicists is like, we run the hierarchy to a given level given by our computer, and then we fix Hilbert space and we look for violations. And we see that up to numerical precision, they close. And we believe that we have the optimal strategy. But extracting the strategy from the moment matrix is not, we know how to do it sometimes in some cases, but it's not easy. To square root of 2? In the CHSA case? I don't remember now. If you give me some time, I will let you know, okay? But it's not difficult, I don't remember. No, wait. Yeah, we need to think about it. But okay, if Miguel Navascos was here, he will tell you immediately, but I'm not as smart as him. So yes, I mean, there is a way of doing these things. But usually this, I mean, to invert the problem, it's something in which there is, the exercise in the afternoon, it will be sort of related to what we are discussing, okay? So usually the fact that you have a quantum realization doesn't mean that you can extract out of this the state and the measurements, okay? So if you look at, you remember the probabilities in the quantum case? You have measurements and state. You have different objects that you combine together to give you the probabilities, okay? So it's not a one-to-one map. There are many different ways of getting from a state and measurements some probabilities, okay? So this is why extracting the state and the measurements from the probabilities is usually hard, yes. Okay, so now I will conclude this part. I focus more on, I wanted to motivate you to look at these things. And so now I will focus on the last part, on an application in which we are working. We also have a paper with Vic. We had a paper with Victor, and we have one more in preparation on how to use this in a different context. And perhaps this is for you to understand that, again, many problems in quantum physics are non-commutative polynomial optimization. Okay, and for instance, in many-body physics, you have many. So what is many-body physics? So this is something in which many physicists are working on. So it's like you prepare in labs, and you prepare systems of many quantum particles, many atoms, and for instance, and these particles are interacting. And you want to understand these properties. So for instance, because there are problems like in quantum chemistry or, for instance, to the design of materials in which you want to understand how atoms interact with each other. And of course, atoms, you have many, and then you have many, it's a many particle problem that is hard to characterize. So what are the typical paradigmatic problems in this situation? Are not Bell inequalities now, it's something different. So for instance, you have atoms that interact with a given, have some given interactions, and you want to understand what is called the ground state, so the state of minimal energy. So usually particles are arranged minimizing the energy. So the natural configuration is the configuration in which they minimize the energy, that is the ground state. And you want to find, say, how electrons will be organized to minimize the energy, and this is found in the ground state. Okay, this is a paradigmatic problem of many-body physics. Okay, or for instance, sometimes you have particles that interact, and they have a steady state. You have probably, you know about Markov processes, and they have a steady state, no? So we have the same. You have quantum particles that interact, and if you let the system evolve, it will converge to a steady state, and you want to understand the properties of the steady state. And there is one that I won't discuss here, but also people are interested, is that you have particles, you want to understand how they dynamically evolve. This is harder, and I'm not going to discuss. Okay, so you may want to understand how they arrange to minimize energy, what is the stationary state of an evolution, or even how they evolve to reach this stationary state, or how they evolve in general. Okay, these are problems in which physicists work a lot. So why is this problem difficult? Well, there is something that sometimes people call the course of dimensionality of the quantum complexity barrier. Okay, so if you look at the problem and you want to be rigorous, okay, you have a system of many quantum particles. Let's say the particle is the simplest you can think of, it's dimension 2, but you have n. Well, things composed with the tensor product. So you compose things with the tensor product, you will see the dimension grows very fast, exponentially. So this means that if you try to describe the state of this large quantum system, you will need an exponentially growing number of parameters. This makes the problem difficult. Okay, you can even store in a memory of your computer, you can store the state of 30 particles, 40 maybe, not more than that. Okay, so you cannot put them in your computer. Also, let's assume you say, okay, no, what I'm going to do, I'm going to make an experiment and I'm going to measure what is in the experiment. Well, you cannot do that because you need to measure an exponentially growing number of parameters. Okay, there is no time for you to measure all the parameters you require. It's an interesting exercise, okay, because now we are in a situation in which we have systems and we know that in principle to have a full description, we need an exponentially growing number of parameters, and we'll never have access to that, okay? So we have to understand how to deal with partial information. So you have exponential number of parameters. In principle, in practice, you have a polynomially growing number of parameters. You have to use this partial information to make predictions about your system. So this is the problem. Okay, so we are forced to deal with partial information. Okay, people prepare these systems in the lab, okay? So, you cannot measure all the parameters. It's just impossible. Okay, so I think something that I want I start going along these lines is that, okay, maybe Hilbert spaces are not adequate to go into that, okay? Because if we stick to Hilbert spaces, the dimension is going to grow exponentially, and we are never going to see all these degrees of freedom. It's impossible. We don't have time. We don't have memory to store all these numbers. So I think the language of moments and relaxations, okay, making this outer approximation might be useful in this many-body context. Okay, I know the relaxation is not the full answer. It's partial information, but maybe it gives me a language in which I can pose problems and in which I can still reach conclusions about my system. Maybe not fully precise, but at least I can scale things up because I can relax and put things into a moment matrix. If I choose the right monomials, it's maybe something that I can put into my memory of my computer. Okay, is it clear what I'm saying? I'm going to relax problems so that I can scale up things and forget about the exponentially growing number of parameters. So I'm very much interested in this perspective, and I think moments and relaxations and polynomial optimization might be a good language in this endeavor, okay? As it was in the device-independent scenario. Okay, so in the device-independent scenario, we intentionally decided to work without Hilbert spaces because we understood that assigning a Hilbert space to a device was potentially a security loophole. Okay, so companies were thinking that they were doing qubit protocols. They were not doing qubit protocols, and that was a security loophole exploited by the hackers. So we made protocols without assigning a given Hilbert space. Here, to avoid this exponentially growing number of parameters, I want to assign Hilbert spaces. I don't want to work with Hilbert spaces because if I do it, I will have an exponentially growing number of parameters. There, it was very convenient. I hope that it will be convenient here as well. This is more recent research. Okay, so this is what I wanted to tell you about. Is it clear my motivation? I want to avoid this exponentially growing number of parameters, and I want to do it using relaxations and moments. Okay, so what is the paradigm? One of the most paradigmatic problems in many-body physics is I want to obtain the ground state of a many-body system. What does it mean here? Is I want to find the state of, I want to find a particular state, which is the one minimizing the energy. I will go into the formal derivation of that. But actually, you don't want to find the ground state because you cannot even write the ground state. The ground state is a huge vector with many parameters, okay? You're never going to find it. So actually what people want to find is, they want to find, say, properties of the ground state. So you want to find, okay, in the state of minimal energy, will my state be magnetized or will conduct energy in a more efficient way? Or you want to understand properties of the ground state, not the full description. You want to understand some properties that are of your interest. So we should abandon this idea that we'll have the full quantum description because it's impossible. So let's consider a situation in which I want to understand a property of the ground state, say magnetization. Okay, so what is the formulation? I have a system made of n particles, and I have an operator which is the Hamiltonian. Okay, it's a polynomial operator. Okay, and I want to find the state of minimal energy, and for this state I want to compute another quantity, which is say the magnetization, which again will be a polynomial. So here I'm working with qubits, spin 1/2 system. I will work with the Pauli basis. I'm assuming that everyone knows what is the Pauli basis. I can express any operator as a linear combination of Pauli and tensor product of Paulis. This is what I'm going to do. I can also do it for other choices of systems, okay? We are used to work with Paulis and qubits in quantum information theory. So what is the problem I want to solve? I will be given the Hamiltonian, that is the operator associated to energy. I want to find the minimum of this quantity. This will give me the ground state energy, and this will be the ground state, the state of minimal energy. You see, I have to solve this problem. Once I solve this problem, I will have the state I'm interested in. And once I have the state, I can compute other quantities on this state. Okay, I hope you follow even if you never saw quantum physics after my lectures, okay? So I want to solve this minimization, and for the state that gives me the solution, I want to compute other properties of this state. Okay, so what is, in principle, what I have to do? I have to find the minimum eigenvalue of this operator. Okay, once I have it, I have to compute this quantity. Okay, nice. Of course, you can solve this exactly. What is the problem with that? Is that, okay, finding the minimum eigenvalue of this operator is hard, okay? It grows exponentially with the system size. So you can do this for systems of a given size, like, again, 30 qubits, 40 maximum, okay? Otherwise, you should stop doing this. So what do people do? People like Matteo, who is sitting there and who will be talking about this, okay? So I'm introducing part of the things he's going to tell you. Yes. So they say, no way I can solve it exactly. But I have good reasons, or, okay, you may argue about whether they are good or not, but they will tell you, look, here, this optimization has to be over all possible states in my Hilbert space, okay? Here, the Hilbert space is fixed, but it's very large, okay? It's fixed, but large. So I'm going to restrict this minimization to a subset of all possible states. Because they have reasons to do that, you may discuss about them, okay? Maybe for reach an agreement, maybe not, but they make a choice. And then instead of solving this brute force minimization, they solve this easier minimization. They find a ground state energy. Okay, you don't know whether it's the ground state energy, okay? But they hope that it's close to the actual solution. They found a state. the ground state, but it's not the ground state, okay? It's a state in this subset that minimizes the energy. And they hope that this state is close to the solution they are looking for. And they use this state to compute the quantity. Okay, and it happens that this choice of subset of states is much smaller, and you can reach much larger system sizes because they have very nice tricks to do these calculations. Okay, so most of the many-body physics literature is based on what is called variational methods. Tensor networks that Matteo will explain is an example of a variational method. So they restrict the optimization to tensor network states. They use do for tensor network states, and they compute things for tensor network states. Okay, so just to summarize, if you do an exact treatment, of course, you get rigorous results, certified results, but you won't go very far, okay? You have 30, 40 qubits maybe. If you do a variational method, you can go, in some systems, you can go very large, hundreds or even maybe thousands. Okay, Matteo knows better than me how far they can go. But okay, you cannot trust the results, okay? Because it's just an estimation of your number. You don't know how close you are to the given value. For you to understand, if this is the energy and this is the ground state, in variational methods, you look for some states and you stop. Well, you don't know if you are here or you are there, okay? You just find a value in a subset of possibilities. It's like local minima, okay? You don't know where you are respect to the ground state. I mean, they achieve amazing results. I'm not saying anything, especially if Matteo is here, he will get angry with me, okay? But it is a fact that you have no control about how close you are, rigorous control about how close you are to the solution. Okay, so polynomial optimizations, and now I'm selling the product, so I will come into that, give you scalable ways of getting certified results. Not as scalable as variational methods, unfortunately, but it's a sort of intermediate regime. You get system sizes larger than exact treatment, but with rigor, okay? So you can have certified bounds on the quantities you are interested in. So it's a valid possibility, I believe, okay? We had this paper last year for ground state, and I'm going to tell you about these things. But there is a lot of things to be done to make these systems really competitive, if it's possible to make them competitive, okay? This is at the moment open. So I'm going to tell you how we do that using the language of polynomial optimization that I hope you are familiar with. I know it's after lunch, so things are demanding, but okay, let's see if we can go together on that, okay? And I will do it for these typical spin problems. So you have a Hamiltonian. It's an operator made of spin operators. So you have these typical Paulis. And the interactions among the spins are given by these coefficients, okay? So this is a typical Hamiltonian, okay? It's a polynomial of Paulis. Okay, so I'm still working with polynomials. Quantum physics gives you many polynomials over operators, okay? So this is a particular instance. A Hamiltonian is an operator made of Paulis, so I can interpret it as a polynomial of Paulis. Good. So if now I apply non-commutative polynomial optimization, the techniques I was telling you about, I will minimize this quantity, but I will do it through relaxations, outer approximations. So now I will get lower bounds to the minimum. Okay, so I can do that. So how to interpret these things? The problem I want to solve is this one. Okay, minimize psi, h psi. If you act with the state on the operator, the state can act here. Okay, these are just numbers. So you act here. So this is the problem you want to solve. Okay, this problem looks easy. Okay, you only have to optimize a combination of these. These are now become numbers. They are expectation values, okay, of a state acting on the operators. So why is this problem difficult? It's because these numbers are not arbitrary. They have to come from a global state for n qubits. Okay, so this is a problem I want to solve. I hope you understand what I did, okay? I just took this, I put the state here, and I act on the states on these numbers here, and this is what I'm showing here. Okay? So these are, I'm going to call them quantum moments. These are numbers, expectation values that you can get when you implement these Paulis on an n-qubit state. Okay, so this diagonalization problem now looks simpler because I only have to optimize this combination of these numbers with the only constraint that these numbers have to be obtained. I should be able to obtain these numbers by taking the expectation value of a quantum state on these Pauli strings. Is it clear? I feel that I'm using quantum terms, but I hope more or less you understand what I'm doing, okay? So it's no longer an exponentially growing operator, but it's just some combination of numbers. The only constraint is that these numbers have to have a quantum realization in an n-qubit system. But this looks innocent, but this is why the problem is difficult, okay? Characterizing expectation values of Paulis that come from an n-qubit state is very difficult. Okay, it seems like I'm hiding the complexity in the definition of this set over which I minimize. So what you do in this polynomial optimization approach is like, okay, you replace this minimization by another minimization in which you minimize over a set of moments that contains the set of quantum moments. And then you will get a lower bound to the solution you are looking for. So if you want a representation again, it's always an outer approximation. It's again polynomial optimization, maybe a bit hidden here. This is the problem I want to solve. The complexity comes from the fact that these numbers, this set of numbers, is hard to characterize. Here, for simplicity, I draw it as a very simple object, but it's not, okay? So what I do, I replace by an outer approximation to the set of quantum moments. Before it was quantum probabilities, but quantum probabilities, quantum moments is the same, okay? And I replace by an outer approximation. So this I can solve through an SDP. This I cannot solve through an SDP. I solve this problem, I will get a lower bound to the ground state energy. Okay, so I'm doing all the time the same trick, okay? I'm replacing a quantum problem by an outer approximation and getting a bound to the corresponding solution. Yes?
So with the A1, we have a hierarchy, other approximations that gets arbitrarily close.
Yes.
With this one,
You can make it convergent. In this case, it's even better because you don't optimize over the operators because they are fixed, okay? In the Bell inequality, the operators could be in a given space. Here, I'm fixing the operators, okay? So convergence, it's even, you achieve convergence in a given finite level of the hierarchy. But it's very high, okay? So it's exponentially high in the size of the matrices. Yes?
It's a lower bound.
Yes.
How sharp is the lower bound? That's interesting because if I tell you like something which is far away.
Yes, well, you will see some numbers. Yes. Yeah, sure. Okay, so the good thing, using the hierarchy in this context. Yes. Yeah, sure. This is one of the first uses of the hierarchy is like you come with your methods and you give me an upper bound. And you want to know how close you are, okay? And I come with my methods and I give you a lower bound. Well, now we have control about how close we are, okay? We don't know whether you are good. Probably you are better than me, okay? Because usually the variational methods in practice seem to work better than but yes, we have an energy window in which the ground state is, which you didn't have by variational methods alone. And you don't have by relaxations alone either, okay? Because relaxations give you a lower bound and variational methods give you an upper bound. Together, they give you an energy range. No, this is arbitrary. It works for any. Yeah. Yes. Okay. Okay. I hope you understood what he was saying. Is like they do variational method. They approximate from the interior. You can understand that what this. Okay, now it's coming. Yes. So you want to solve the problem over the set of quantum solutions. What these people do, they solve it for a subset in the interior. By definition, you get an upper bound to the energy. It's a subset of the possible solutions. We do it from an outer set, you get a lower bound. And if you put them together, you will get a range in which the ground state energy lies, okay?
Sorry.
Yes.
This is not a qubit set, right? This is now.
This is the quantum moments, yes. Yes. No, because it was the same before. So And there is no Hilbert space also in Bell inequalities. You also deal with quantum moments, okay, with these numbers. You see, when you make the bracket, you have the expedition.
Space of non-commutative, right? Or you go towards MQ, but in variational methods you pick a region out of the Hilbert space.
Yes, but here I'm not representing this. So what I'm representing are the Pauli strings that you can get out of a tensor network calculation. This is the space I'm showing here. I mean, also, if you give me the tensor network description of a state, you cannot compute all observables acting on that state, okay? I can give you a very complex entangling observable, and you will never be able to compute it with your tensor network state. You can compute, for instance, Pauli strings. Well, this is what I'm showing to you. So here, if you want, these are the expectation value with your tensor network calculations of the operators appearing in the Hamiltonian. It's a projection of your tensor network to these Pauli strings. This is what I'm representing. Okay, so variational methods give you rigorously, all what you get is an upper bound on the ground state energy and relaxation given a lower bound. Okay, so in this paper, we show that actually you can do more, and this is some of what is interesting about the use of these relaxations, okay? So again, I will repeat what I say. Your goal is to find a property of the ground state, and basically what you do, you minimize, you get the ground state, and you compute the property you are interested in. Variational methods, you optimize over a subset, you get a state, hopefully close to the ground state, and you compute the property with this state, hopefully close to the value you're interested in. You have no clue. With relaxations, you can also put this in your moment matrix, and you don't get a state because it's an outer approximation, there is no state, but you can get a value, a candidate estimation for this value, and again, you don't know how close it is, okay? You can always do, I mean, you can have expectation values here. You don't know whether this is achievable in quantum physics, but it's an estimation. Okay, this is what people knew. Okay, what we realize is that if you put the two things together, you can use information from the variational method with polynomial optimization, then you can bound any quantity in the ground state. Okay, so now I can give you bounds for any quantity of interest in the ground state. And this is something new. And this is what I want to tell you about. So actually, all what we use from the variational method is the energy upper bound they get. Okay, remember, they explore this and they get a value, and for sure you know that the ground state has an energy smaller than the value they computed. So how do we do that? Okay, so remember, the problem the energy problem is given by this, and we relax and we replace the quantum points by some expectations that satisfy some moment matrix constraints by these relaxations that I briefly told you about. Now, you can play this trick for any quantity of interest, okay? You tell me an operator, I can always write an operator in a Pauli basis, and I can always write it as a polynomial of some Pauli's, okay? And then I did this for the Hamiltonian, but I can do this for any operator. I can always write it as a combination of Pauli's, okay? I can always do that. So I'm going to solve this problem. I want to minimize the expectation value of your operator, and I will do that. So I take the Pauli decomposition, I put it here, and I have, again, let's say a polynomial of these operators, and then a combination of the moments of the state acting on those operators. I'm doing the same as for the Hamiltonian, as for the Bell inequality, but now for this operator of interest. Okay, if I do it like this, I'm going to obtain trivial bounds, okay, because I'm not saying anything. This is optimization over all possible states. Okay, I will take the information I get from the variational method, and I will optimize this not over all possible states, but only over those states that have an energy smaller than the value I got on the upper bound. And then if this number is good, this minimization will be over a smaller set of possibilities, and I will get good bounds for the quantity of interest. So is it clear what I'm doing? I'm just taking polynomial optimization I can apply to any operator. I take an operator of interest, and I use the extra information I get from the variational method to impose that I don't optimize over any state, but only over those states that have an energy smaller than the value I computed with my variational method. Okay, so what is the problem? And this is the problem. So I have to minimize this polynomial over these constraints with the extra constraint that the energy is smaller than this value. This is again a polynomial constraint, so everything is polynomial and all the relaxations, streaks, moments apply. If I apply the minimum, will get a lower bound. If I apply the maximum, I will get an upper bound because so I get a lower and an upper bound on the quantity of interest acting on the ground state. So now you tell me, oh, I want to know this property of the ground state. I run this, and I can give you certified bounds on the quantity. Whether they are tight or not, well, this depends on the problem, but I can give you this recipe. And this is impossible by variational methods, by relaxation. So you have to, okay, there are some relaxations now that can do that, but in our paper, we have to put the two methods together to have this certification. Okay, now how does it work? Here we also worked with Victor and Ji Wang, who was at the time postdoc with Victor. And he was really very important to make a calculation for large systems. So we took what is called a Heisenberg model. Okay, this is a quite famous Hamiltonian and here it's a line. So you have the qubits and they interact, okay, in the line to nearest neighbors. Okay, you see here the Hamiltonian is just Pauli's. Pauli I talks, qubit I talks to qubit 1 plus 1, I plus 1. And you have interactions according to the X, Y, and Z Paulis. Okay, I mean, at the very end, this is not so relevant, I would say, just a Hamiltonian, okay? And for instance, here you can see and we also took a slightly more complex system in which you have interactions to nearest neighbors and to next to nearest neighbors, okay? You see I and I plus 2. Okay, this is the energy for you forget about this orange line here. This is the energy for the variational method, what Matteo does with tensor networks, and this is the lower bound we got. Okay, you almost see no gap, okay? So here, it works very well. So I can tell you, this is the energy, basically. And this is for this next to nearest neighbor. Again, you see, it's pretty good, okay? The difference between the upper and lower bound. This is for the energy. Now, we also computed some expectation values of 2 Paulis. Okay, this is what the variational method gives me. I don't know whether this is correct or not, but we can derive these upper and lower bounds. Now, is this good or bad? Well, I don't know. The difference is 0.02. Is this good or bad? I don't know. Here it's for sure good, no? So here we are basically solving the problem. This was for size 40 or 60 qubit, I don't remember anymore. Okay, but you can also do it for 100. Or G1 can do it for 100, okay? Yes, but okay, I mean, I think it's decent. Or for instance, we had also this for another quantity. Okay, so for instance, here I can certify something to you, okay? So here what I'm doing, I'm computing the ground state, and I see how the properties of the ground state change with varying this parameter J2. So what I can tell you that this quantity here is positive because the lower bound is positive, and here is negative because the upper bound is negative. So I can certify to you that the ground state, there is a change of sign in this quantity. And this is certifiable, okay? Because the lower bound is positive and the upper bound is negative when you cross this region. This is something impossible to obtain by any other method. So sometimes at the very end, maybe the exact value of this quantity doesn't matter. Maybe it matters more whether spins are aligned or anti-aligned or things like this. This gives you more information rather than something is 0.753. And we also went to 2D. So these are systems that are according to a square lattice, okay? These are really difficult, even for people like Matteo, also for us. But okay, we gave some curves. You see here, this was obtained with Monte Carlo, and this was our method. We have a larger gap, probably. I suspect that they are better than us, but there is a gap. Again, is it large? Is 0.005 in the energy? I don't know. Okay, but there is a larger gap than in the previous case. And again, we can do similar things, okay? So we can compute upper and lower bounds. Things work worse in this case. Still, okay, is it large to have a difference of 0.08? I don't know. I think it depends on the problem, yes. For the, okay, here, okay, now G has improved the the code, and he's able to solve. Okay, in this case, he can solve because the system has symmetries and it's sparse, okay? He can solve 16s times 16s, 256 qubits, which I find really impressive. But this is happening because the system has symmetries and it's sparse. So again, he does it for a given level of the relaxation. You can do it for lower levels of the relaxation. You will get larger sizes, but the gap here will increase. So it's a matter of precision and yes. Okay, so but for instance here, we can certify that this quantity changes sign in this 2D system around a value that is between 0.45 and 0.60, because here the lower bound is positive and here the upper bound is negative. So you can extract information about some quantity behave in the ground state in a certified way.
Tuning parameter to UQ.
Yes, this is what I was saying. So we can put more, you have these relaxations, the outer approximations. I can do for other tighter outer approximations, and I will improve the bounds. But of course, it's like your bond dimension somehow is the level in our relaxation. It's an analog. But I mean, something that I think is interesting is like, so far, the way we were growing the relaxation was blindly. We're putting monomials for a given degree, okay? This is for the experts. I think we should understand how to put the physics of the problem into how to increase these relaxations, and we are missing this. So we're doing systematically, and well, okay, I don't know, maybe it's a bit.
What bound or the action bound?
No. No, I think we are missing, like I think your variational methods, they have been developed for years, and you have a much better understanding of what's going on. Also because in your case, you are restricting the search, but to set of physical states. While in our case, it's an outer approximation, so our understanding is worse, I would say, in this sense. So we need to develop a physical intuition about what's going on in these outer approximations. Well, maybe I'm talking too much now about. Okay, and we did something similar for I don't have time, I believe, for this, but I will just simply say that also in quantum physics, we have something analog to what you have with a Markov channel, and you want to find the stationary state of your Markov channel. So you have a system evolving with an environment, and you want to understand what is the steady state of the evolution. And a very typical scenario of this problem is given by what is called a Limbladian for the experts. So basically, you want to find the evolution of your state is given by this operator acting on the state. So the steady state is the one in which the state stem does not evolve. So it's the state that is the zero of this operator. Well, this is a polynomial equation. So as soon as you see a polynomial, you should call me, okay? Because then we can come with our techniques and we can give you some recipes to solve it. So we understood that this is, again, a polynomial problem, so we can address it with our techniques. I don't have time to tell you about this. And okay, the results are worse in this case, but you can also get bounds on the properties of your steady state for large systems. Okay, so I think there's a lot of things to be done here. While the use of non-commutative polynomial optimization in this device-independent approach, I think it's well understood here. We need to really understand this. In particular, we are very, very far from reaching system sizes comparable to variational methods. So I think in general, okay, in some cases we can, if system is symmetric and sparse, I think we are getting competitive numbers. If not, we need to understand better how to use these properties. And I think it would be nice because you will reach something that I call certified many-body physics, okay? So you will be able to reach predictions about large systems that are with rigor, okay? So you will have certified and scalable predictions for many-body systems, which is something that you cannot do with the present techniques. Okay, so with this, I conclude. I just wanted, I believe I started at 2, no? Yes, I think it's okay. So I just wanted to motivate you. I started in quantum information theory, protocols, device independent. Quantum physics is a source of polynomial optimization instances over non-commutative variables, okay? So non-commuting variables. Okay, we have many ground states, randomness, Bell inequalities. This is what I described here, but there are many more. Okay, and for those, you end up optimizing over operators subject to some polynomial constraints. And this is why it's a natural language for this formalism. I didn't have time. If you want, I can also tell you about some uses of this non-commutative polynomial optimization in quantum foundations. I focus on protocols, and I was more briefly telling you about the many-body physics. So I think there is still a lot of space for new applications and methods. So I'm also inviting you to give a look at these problems if you are interested about this. And that's all from my side. Thank you very much for your attention. Wait, I went too fast. Yeah, sorry. I clicked too many times.
Remind us the M's. I kind of got a little bit.
Yes. So what is a ground state problem? Okay, you want to find the state of minimal energy for this operator, right? So I'm going to rewrite in an equivalent way. So you want to minimize psi h psi. Okay, this is the same as saying I want to minimize j times this number and these numbers over those numbers. Okay, let me write here. I will give you an example. Okay. This is a problem you want to solve. Okay, there is a tensor product here, but okay. So now I put this state on the operators. This is just a minimization over, it's just some numbers, right? These are numbers. And these are numbers. So why is the problem difficult? It's because characterizing this set, what is the set? Those numbers such that there exists a state such that so the problem is difficult because finding these numbers is difficult. Otherwise, it would be super easy. It's like, for instance, I give you this Hamiltonian. Okay? So, okay, you would be tempted to say, okay, the ground state is equal to, okay, not this one. This is not the one I want. Okay, what I'm saying, okay, forget about this. It's not a good idea. Okay, the problem is difficult because characterizing these numbers is difficult. This is connected to the marginal problem in quantum physics. You know about these things, so, well, it's not easy. Because if it was easy, this is just a linear combination of some numbers, okay? There is no Hilbert space, no exponentially growing, okay? The problem comes that characterizing this set is difficult. Okay? Okay, so the numbers here, I call it MQ. So characterizing this set is difficult. This is why the ground state problem is difficult. So what variational methods do, they don't explore all the quantum moments, just a subset of those, okay? So what they do, they construct some states, a subset of those states, and for those states, they compute these numbers, and they place them here, and they minimize. Well, this is what I'm doing, okay? And they find this energy. But they should find this energy, because this is the actual solution, okay? So again, what is the ground state? It's a linear combination of the quantum moments, so it's a hyperplane. It's like a Bell inequality, okay? It's a hyperplane. You want to find that one, which is when it becomes tangent to your physical, quantum physical set of moments. And variational people, they do it over a subset, and they hope that this point is close to the solution they are looking for. An extra problem they have is that the set they are optimized over is not convex. So they may also have local minima. This is why they have to grow the bond dimension to get some confidence that, okay, whatever, they have some techniques to do it, but it's not convex. What we do, we relax, we outer approximate the set of quantum physical solutions. In our case, the set is convex. And then we also hope that we are close to the ground state.
So an SDP right there.
Yeah, all this, you can get closer and closer, yes.
What happens with dual of this? This would be an upper bound on another side, but now this other sides, we use the variational diagonal form. So
Yes.
Is that like a relation between, probably not a relation, but what is better as taking as an upper bound?
Yes, okay, so, I don't solve the original problem, but I solve the relaxed one, okay? So here I have some feasible points, okay? So I know that the solution to that is a lower bound to that, okay? Because you see it here, no? It's an outer approximation. So any feasible point is an upper bound to the lower bound, so it's bad. But if I compute the dual of that, it's a lower bound to the lower bound, so it's a lower bound. I'm not sure if you understand what I'm saying. I can compute the dual of this one, and it will give me a lower bound to the lower bound. Okay, self-valid lower bound. But what I do in the SDP, I close the gap between the primal and the dual, okay? So in the SDP, I solve this problem, which gives me the lower bound. I'm sort of repeating my... Okay.
That were
Yes.
you have SDP.
Well, it's the same. I adapt it to the problem. I adapt it to the polynomial I'm interested in. I mean, there is only one hierarchy that applies to any polynomial optimization. Being minimum or maximum doesn't make any difference, okay? It's just the minimum is the same as the maximum. So it's the same hierarchy. I sometimes use it to compute minimums, and then I get a lower bound. I sometimes use it to compute maximum, and I get an upper bound. And I compute it to any polynomial made of Paulis. It's just a polynomial. There is one single hierarchy. This is what I'm telling you. This is a formalist that you can apply to many problems. You give me the polynomial, and I come.
To this gap problem, so do you observe duality gaps?
No. Yes. What do you need for that? That there is a feasible point, no? Yes. I would say for most of the physical problems, I wouldn't expect to have any.
Question of the bosonic system is that the NPA hierarchy does not converge for
No.
Why?
Because the operators are not bounded. So in principle, if you have a bosonic system, like for instance, in the standard formulation, people don't bound the energy. And then operators are not, you have, I don't know if you know about bosonic system, but you have what are they called the X and P operators. And X can go from minus infinity to infinity. And then you have this, yes. Here, I don't need for the Hamiltonian because I'm dealing with, okay, so this is something where I believe we need to understand things. I put them in the same formalism, but the Bell inequality is not the same as a Hamiltonian. If you remember what I did for the Bell inequality, I was writing so I was optimizing over the state prepared by Alice and Bob and the measurements they implement. In the Hamiltonian, the operator is given by the Paulis, it's fixed. Okay? So the problem is somehow bounded by construction because I'm dealing with Paulis. Okay? And then, well, it's bounded because also these things are bounded. So, but there is a difference that I think we have not exploited yet, which is a Hamiltonian problem is a polynomial problem, but I know the polynomial I'm optimizing over. I don't need to look for larger, this problem is decidable because this Hilbert space is fixed, is given by the Paulis. The Bell inequality problem is not decidable because I don't know even the Hilbert space that I'm working on. I'm relaxing the two things, but here it's not exactly the same. I mean, you can apply the same formalism because they are polynomial over operators, but there is a difference. Here, the operator is given and you are not going to touch it. Here, the operator is not given because it varies with the measurements that Alice and Bob implement. I'm not sure if I'm explaining myself. In any case, all these problems are phrased in terms of bounded operators, and then I know that things converge. I add these constraints in my SDP because I know from the physics of the problem that the operators are bounded. The problem is that with bosonic systems, I don't have any constraint that looks like this, so my operators are unbounded. So in these problems, I add constraints coming from the physics of the problem, and I'm imposing that they are bounded. A Pauli matrix is bounded, okay? So this is a polynomial of Pauli matrices with bounded coefficients. So it's bounded, everything is bounded.
You are saying this relaxation is convergent.
Yes, this. Yes, this or this is the same. Huh? So this is convergent, yes.
Optimization when you have unbounded domain support, still you want to minimize the square sieve. It goes to infinity at infinity. So this is also the case for your bosonic problems.
So in the worst case, no. So we don't. For instance, if you okay, I haven't worked so much on these things. For instance, if you bound the energy, you can say, okay, I'm a physicist, so energy cannot be unbounded. And then since the tails cannot be brutal, to infinity, probably you will have something like convergence. But what I'm saying is that usually in the standard physics formulation, we don't impose these things. But I would. I think if things behave in a reasonable way, you will have convergence. But yeah.
Bosonic systems is bounded as a whole. Yeah. Always bosonize spin operator, for example, from some bosonic operator. But the bounds of it will not change.
I think in a way you will be imposing some sort of bound on the energy, by fermionizing things. Yes. Yes. Yeah, but probably you will have an energy within a given. I think. Yeah, okay. It depends on the specificities of the problem. The only thing I'm saying is that if you have unbounded operators, I cannot prove convergence. Okay, this is the only thing I want to say. And there is no. Okay, so we know examples in which there is no.
Thank you. We have